and to become inverse of that standard matrix, that formula is adjoint of standard matrix upon determinant of the standard matrix. Okay, so we already find adjoint of that standard matrix, that is this one, and determinant is -1. So basically we have to multiply all the elements with -1. So 4 minus 2 minus 3, minus 11 6 9, and minus 12 7 10. Okay, so that is equal to the standard matrix of T inverse. So now we can define T inverse x1 x2 x3 is equal to 4x1 minus 2x2 minus 3x3 minus 11x1 plus 6x2 plus 9x3, that is second row of this matrix, and minus 12x1 plus 7x2 plus 10x3. Okay, let's see next example. In each part determine whether multiplication by A is one-word linear transformation or not. So clearly we have to convert that standard, we have to convert this matrix in row echelon form, and let's see how many non-zero row in that standard matrix. From that non-zero row we can find rank of matrix, and from that we can find nullity of T. Okay, first one is very simple. First row is 1 minus 2, second row is 2 minus 4, third row is minus 3 6. So we have to multiply first row with -2 and add into second row, that is 0 0, second row becomes 0 0. We have to multiply first row with -3 and add into third row, so third row becomes 0 0. So rank of that standard matrix is 1. Okay, and nullity of that standard matrix is also 1. Why this is 1? Because dimension of the domain is actually 2. This transformation is actually from R2 to R3. Okay, because standard matrix is from 3 cross 2. So clearly you can see that transformation is definitely from R2 to R3. So dimension of domain is 2, because the domain is equal to R2, so dimension of domain is 2, and here rank is 1. So nullity is actually rank dimension of domain minus rank. So 2 minus 1, that is 1. So nullity is 1. So clearly T is not 1 1. Okay. Next example. Here another matrix. Again we convert this matrix in row echelon form. So first row multiply with -2 and add into second row, that is 0, -7, -8, -10. Second row become, third row become, we have to multiply first row with 1 and add into third row, so third row becomes 0, 6, 5 and 7. Okay, now in second row, first row leading entry 1 and below that leading entry we have to make 0, we make 0. Okay, in second row what is leading entry? -7. Okay, so first of all we make that leading entry become 1, so we multiply second row with -1 by 7, so second row becomes 0, 1, 8 by 7 and 10 by 7. The first and third row is same. Okay, first and third row are same, and then we multiply second row with -6 and add into third row, so that process is here. Okay, so you can see all of 3 rows are non-zero, so rank of that matrix is 3 and nullity is 1. Again, why nullity is 1? Because dimension of domain is 4, because this transformation is actually from R4 to R3. Okay, this transformation is from R4 to R3. We know that from if T from Rn to Rm, the standard matrix is in form of m cross n for that given transformation. So here standard matrix is in form 3 cross 4, so definitely our transformation is from R4 to R3. So dimension of domain, so domain is R4, so n is equal to 4, rank is 3, so nullity is 1. So again T is not 1 1, because T is 1 1, nullity should be 0. So here nullity is 1, so T is not 1 1. Next example. This is a good example. See, it's quite simple. In each part use the given information to determine whether the linear transformation T is 1 1 or not. Okay, first is T from Rm to Rm operator, nullity is 0. So by definition you can easily say that first transformation is 1 1. Okay, because clearly nullity is 0, so T is 1 1. We know that T is 1 1, then kernel of T is equal to singleton theta and nullity of T is equal to 0. That 3 statements are equivalent statement. I again repeat that 3 statements are equivalent statement. If one of the prove, then other 2 are automatically we can prove. Okay, So again T from Rm to Rm, nullity of T is equal to 0. So T is 1 1. First transformation is clearly 1 1. Now second example, T from Rn to Rn. Here rank of T is equal to n minus 1. Okay, rank of T is equal to n minus 1. So here nullity is 1 because domain is Rn. So dimension of that domain Rn is equal to n and rank of T is equal to n minus 1. So clearly nullity is 1, and if nullity is 1, this transformation not a 1 1 transformation. Okay. The third one example is very good example, T from Rm to Rn. Now n less than m. Okay. So in C you can see what is our standard matrix in this C, n cross m, because transformation T from Rm to Rn. So our standard matrix is from n cross m. Okay, and where n less than m. Okay, n less than m. So maximum rank of that standard matrix is n. Okay, maximum. Okay, maximum rank of that standard matrix is n, right, because our standard matrix is in form of n cross m, right. So number of row in that standard matrix is n and number of column in that standard matrix is m, but the number of row is actually the less than number of column in that standard matrix. So maximum rank of in that standard matrix is n, right, and the dimension of domain is m. Okay, so clearly nullity is greater or equal to 1. Minimum nullity of that standard matrix is 1. Okay, and if nullity is greater or equal to 1, that transformation never become a 1 1 linear transformation, because to become 1 1 linear transformation nullity should be 0, right. So C is not 1 1 linear transformation. And D, T from Rn to Rn, range of T is Rn. So clearly this transformation is 1 1 linear transformation, because range of T is Rn, that means rank of T is n and dimension of the domain is also n. Okay, so nullity is 0, so T is 1 1. Okay, so this 4 example, first one and last one, A and D is a 1 1 linear transformation, but second and third, that means B and C is not a 1 1 linear transformation, right. So here is the solution. First one is 1 1, since nullity if T is equal to 0. Second one is not 1 1, third one is also not 1 1, right, and the last one is 1 1 linear transformation. Now next theorem, if T1, first transformation T1 from U to V and second transformation T2 from V to W are two 1 1 linear transformation, then T2 composition of T2 with T1 is 1 1. Okay, and inverse of composition of T2 with T1 is equal to inverse of T1 with composition of inverse of T2, right. So this theorem is very important. Let's see one another example. Here T1 from R2 to R2 and T2 from R2 to R2, both the transformation defined from R2 to R2 with a linear operator. Clearly linear operator. Why this is linear operator? Because domain and codomain are same, so that's why we can say that it's operator. Given by the formulas, T1 of xy is equal to x plus y, x minus y, and T2 of xy is equal to 2x plus y, x minus 2y. First we have to prove that T1 and T2 both are 1 1. Okay, so for that we use standard matrix for this two transformation. And second one, find the formula of T1 inverse xy and T2 inverse xy. And third one, we have to verify that above theorem, that inverse of composition of T2 with T1 is equal to inverse of T1 with composition inverse of T2. Okay, that we have to verify particular for this example. Okay, generally this is true that we know, but we have to prove this statement particular for this example, right. So first we have to prove that T1 and T2 both are 1 1. So here is a standard matrix for T1. What is the standard matrix for T1? What is first coordinate? X plus y, and in first coordinate coefficient of x and y is 1 1. So first row of standard matrix for T1 is 1 1 and the second row is 1 minus 1. Clear? And what is the standard matrix for T2? Take it first coordinate is 2x plus y. In 2x plus y the coefficient of x and y is 2 1. So the first row of standard matrix for T2 is 2 1. Let's take second coordinate for T2, x minus 2y. In second coordinate the coefficient of x and y is 1 minus 2. The second row for T2 is 1 minus 2. Okay, so here is the standard matrix for T1 and T2. 1 1 1 minus 1 and 2 1 1 minus 2. Clear? So first of all we convert this two matrix in row echelon form. So we multiply first matrix with minus 1 and add into second row. So clearly with only one process that matrix become in row echelon form. In row echelon form you can see that both the rows are non-zero. So rank of T1 and rank of T2 both are 2, because in second matrix also both the rows are non-zero row with one process. Okay, so nullity of T1 is equal to nullity of T2 is equal to 0. Okay, again I repeat, rank of T1 and rank of T2 is equal to 2 and the our transformation from R2 to R2, right? So n is equal to 2, which is actually domain or dimension of the domain. So nullity is equal to dimension of domain minus rank, that is 2 minus 2 is equal to 0. So clearly T1 and T2 both are 1 1. Okay, so first one we prove that T1 and T2 are 1 1. Now we have to find inverse of T1 and T2. Now we know that if we want to find inverse of any 2 cross 2 matrix, it's quite simple. Again I repeat, if we want to find inverse of any 2 cross 2 matrix, it's quite simple. We have to just interchange the elements of the main diagonal. We have to just interchange the elements of the main diagonal. So you can see what is our first matrix, 1 1 1 minus 1, and what elements in the main diagonal, 1 and minus 1. So just interchange that two elements. Okay, so instead of 1 minus 1, that is become minus 1 1. Okay, and change the sign of another diagonal, that another diagonal is 1 1. So when we change the sign, that will become minus 1 1, minus 1 minus 1. So that new matrix become minus 1 minus 1 minus 1 1. Here this matrix minus 1 minus 1 minus 1 1, and then we have to divide it by determinant of that matrix. What is determinant of that matrix? You can see what is determinant of first matrix, minus 1 minus 1, so that is minus 2. Okay, so just divide it by minus 2 of that new matrix. So our new matrix, that is actually the inverse of this standard matrix T1, that is actually the standard matrix for T1 inverse, that is 1 by 2 1 by 2 and 1 by 2 minus 1 by 2. Okay, with the same process, see what is second matrix, 2 1 1 minus 2. So interchange the elements of the main diagonal. So minus 2 2 minus 2 become minus 2 2. Okay, you can see on the screen 2 minus 2 become minus 2. The first element is minus 2 and the next element become 2. Okay, and change the sign of the another diagonal, that will become minus 1. Instead of 1 1, that will become minus 1 1, minus 1 minus 1. Okay, and then divide it by determinant, and the determinant is minus 5. You can see 2 into minus 2 is minus 4 minus 1, so minus 5. So divided by minus 5, our new matrix, that means inverse of that standard matrix T2, that is actually the standard matrix for T2 inverse, is 2 by 5 1 by 5 1 by 5 minus 2 by 5. Okay, so T1 inverse xy is actually x plus y by 2 and then x minus y by 2. T2 inverse xy is equal to 2x plus y by 5 x minus 2y by 5. Okay, next we want to prove that inverse of T2 composition with T1, that is equal to inverse of T1 composition with inverse of T2. For that we have to verify that inverse of standard matrix of T2 multiplication with standard matrix for T1, that is equal to standard matrix of T1 inverse into standard matrix of T2 inverse. Okay. So what is standard matrix of T2? 2 1 1 minus 2. What is standard matrix of T1? 1 1 1 minus 1. Multiply that to standard matrix. Okay. How we multiply? Here is 2 matrix, 2 1 1 minus 2 and 1 1 1 minus 1. So how we multiply? We have to choose first row of the first matrix and multiply with the all the columns of the second matrix. Okay. So 2 into 1 2, 1 into 1 1. So 2 plus 1 3. Then 2 into 1, this 2 into 1 3, 1 into minus 1. So 3 minus 1, that is 2. Then choose second row of the first matrix, 1 into 1 minus 2. So minus 1 and then 1, 1 into 1 1, minus 2 into minus 1 2. So 1 plus 2 3. Okay. So this is our multiplication of this 2 cross 2 matrix. So that is 3 1 minus 1 3. You can see on the screen. Okay. So 3 1 1 minus 1 3. So that is multiplication of standard matrix of T2 with multiplication of standard matrix of T1. Now we want to find inverse of that matrix. Again we have to just interchange. What is determinant of that matrix? 9 plus 1 10. So clearly you can see determinant of this matrix is 10. 3 into 3 9 minus 1 into minus 1 minus 1. So 9 plus 1 10. And when we interchange the elements of the main diagonal, that is same 3 3, and change the sign of the another diagonal, minus 1 1, and then divide it by 10. So 3 by 10 minus 1 by 10, 1 by 10, 3 by 10. Okay. That is our new matrix. That is actually the inverse of multiplication of standard matrix of T2 with standard matrix of T1. And then we have to multiply this two matrix, standard matrix of T1 inverse into standard matrix of T2 inverse.